G'day chemists. Today we're going to look at different types of bonding. Essentially, we're going to keep it really simple and we're going to focus on the basics. Now, a lot of this is going to be revision from year 10, but it's an add-on, okay? So it gets more and more complex as we go. Right, let's get into it. First, anions and cations. Again, other ways to say it, we're saying that so that the ion part is emphasized. So these are, well, neutral atoms have the same number of electrons as they do protons, but atoms with differing amounts are called ions. Now, cations are positive ions. They donate electrons, so they give them away. Now, when we talk about ionic bonding, we're not talking about sharing electrons, we're talking about giving and receiving. So, positive ions, they donate electrons, which means they give them away, and this is why they're called positives. They have more protons than they do electrons, so a greater number of protons than electrons. For example, magnesium 2+ has lost 2 electrons, which means its charge is positive because it's got 12 protons and 10 electrons, so it's a net positive charge of +2. Alright, anions. Negative ions. They receive electrons, so they're given electrons. They have so over here we see they have more electrons than they do protons, a greater number of electrons than they do protons. So chlorine has gained 1 electron, chlorine minus has gained 1 electron. Therefore the charge is negative because it has 17 protons and 18 electrons. So there's a net negative charge. Alright, so let's look at ionic bonding. Now, ionic compounds are not molecules, okay? I don't know if that's something you've been confused with beforehand, but they're not molecules. They are oppositely charged ions bonded together due to electrostatic forces. So, positive and negative attracting really strongly, and they form a crystal lattice. The simplest ones is sodium chloride, and you'll see it makes this sort of box shape. Now that's the basic box shape, but it's a repeating box shape. Anyway, so we'll come back to that. The formula is a ratio, so they're not separate molecules. So even though it says NaCl, that doesn't mean that you ever see one sodium and one chlorine ion joined together. It's an entire lattice work, a 3D structure, crystal structure, lattice crystal, crystal lattice, that has an equal number of sodiums and chlorines. So 1 sodium for every 1 chlorine. So as I say, it's a ratio, it's not separate bonds, separate molecules, it's a ratio, and we call that an empirical formula. So an empirical formula is one that's a ratio. Alright. They're very strong bonds, which means the solids are hard and brittle. Alright, so for example, here's a crystal shape, so it goes down and then out in 3 different directions. That's silicon oxide, which is SiO2, and you see for every silicon, which are the big red ones, so silicon here, like there are two oxygens. Might have to check that one. Anyway, I definitely have to check that one. Tell me if I'm right tomorrow in class. Now, a little note. Polyatomic ions, like nitrate down here, they are covalently bonded, but then they have the charge taken away, or added to, depending on, and they stay as a unit. They never separate within the structure, so they kind of count as one ionic atom. They're a polyatomic, but they count as one. They don't separate. This is how it works. Alright, this is something we'll go over later on, but each of these dots relates to an electron in the outer shell. Magnesium has 2 in the outer shell, chlorine has 7 in the outer shell. Now, this is something called Lewis dot structures, and we'll talk about those later. But they can be drawn the same. We've just drawn them with X's and dots so that you can see which one comes from which. Alright, so if you've got magnesium plus chlorine, so when they're together, magnesium loses its electrons, chlorine gets them, and they bond together because of those charges. But what we see is magnesium, which is 2 positive, so it's 2 plus, so it's got 2 extra protons, and chlorine, which has 1 extra electron. They're bonded together. Now it says 2 there because this is given away 2, and it's given 1 to that chlorine atom and 1 to another chlorine atom. That's why it's got the coefficient of 2. But we'll get into those diagrams later on. That's just to show you how they're sharing. Not sharing, giving away. Okay. Just quickly, nomenclature means naming. So these are our rules for naming ionic compounds. So ionic nomenclature rules. Alright. The cation is written first and the anion second. So sodium chloride. Polyatomic ions with multiples. So you've got, in this case, 2 nitrates. They're written in parentheses with the subscript down the bottom. So you don't ever change that. It doesn't become N2O6. The cations with fixed charge just have the same name as the neutral one. So Na plus is sodium. However, variable charge, and we often see these in the transition metals, they have its regular name with a Roman numeral next to it in parentheses. So iron 3 plus is iron 3, and you've got iron 2. Copper is another one that you'll see a lot of, and we usually deal with copper 2. But yeah, so alright, so that's cations with the, again, you tend to find those in the transition metals. A monatomic anion has a suffix "ide," chloride. The nitrates, so these ones, they have different suffixes, but we'll get to that later. Greek prefixes, not used. We don't need those to tell us how many of each atoms there are, each type of atom, because we can look up its valency and we can work it out. So, for example, MgNO3, there should be a 2 there, is magnesium nitrate. Calcium sulfide, calcium chloride, copper 2 iodide. So there are our examples. We're almost done. Molecular covalent bonds. This is where molecules are found. So molecules are held together by covalent bonds. This is one where you can have O2 and it will exist as just O2. Okay? It doesn't exist in a structure. Alright, so they share electrons to make it stable. The stable shell is 8, this, stable outer shell. And they're not usually opposing charges. So if we've got nitrogen here we've gone for 2, by the way, diatomic elements. So these are elemental molecules, and they're covalently bonded. So nitrogen has 5 in the outer shell, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Again, we've just used dots and crosses so you can see which is which. So the nitrogen here, in its outer shell, they share the electrons to bond it. So you've got 2 there, 3 there, and then it's using 3 from its neighbour as part of its outer shell to stabilise it. And this one has its 2 original ones, then 3, so it needs 3 more, and it's sharing 3 of this one. And that's how covalent bonding works. Oxygen, if we look, oxygen has 6, and this is how you can work it out, by the way, what it's going to be. Oxygen has 6, so it only needs an extra 2, so it shares 2 with its neighbour. And that's how we get oxygen. Now, just to finish us off, there are rules for naming binary covalent molecules as well. Now, binary just means there's 2 types of atoms. Alright, so the element with the lower group, and that's the down columns, element with the lower group is written first. There is an exception. So when oxygen and a halogen, so that's all your chlorines, group 7, the halogen is always written first. So this was oxygen and a halogen. That's your exception. Example, carbon monoxide is CO, because oxygen, it's further along. So if you've got 2 of the same group, right, the one with the highest period number, it's written first. The period numbers are the numbers of the rows. And quickly, why it's called period number is because it goes, that's when So all the trends that go across this way, they reset when they come back across. And then, so it's like a period, a cycle. So the period number, the one with the highest period number is written first when they're from the same group. Sulfur dioxide, sulfur's lower down in its column, therefore it's written first. The second element is named as if it's an anion from our ionic compounds, so it has "ide" at the end. The difference is we use Greek prefixes to indicate the number of atoms. That's how we know how many atoms are in it. We don't use mono for the first one, so the front one, in this case carbon, but we use it for the other side. So this is what they mean. So we've got mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Just quickly, if we're going on with so if you're going non-oxide, so something with 9 oxygen, you won't write non-oxide, you'll write non-oxide. You don't double up on the vowels because it just gets awkward. Alright, that's it for today, and yeah, see you in class.